Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And this video is a continuation of a series of videos on the mean value theorem and Rolle's theorem. And in this video, we're going to actually use the mean value theorem in a couple of instances, both of which honestly are pretty rote. Common that you'll see them in textbooks or something like that. And then in the next video, we'll delve into more important or interesting examples. But this one will just go through the ones that you commonly see in a calculus textbook. So verify that the function e to the negative 2x satisfies the hypothesis of the mean value theorem on the interval from 0 to 3. And then find all numbers c that satisfy this conclusion. Remember, the mean value theorem just tells us that if you're given a function, in this case, e to the negative 2x, something like this, and you're given that continuous function on a closed interval, this case from 0 to 3, and as long as that function's differentiable on that closed interval, so we have a continuous function on a closed interval, and it's differentiable, on the open part of that interval, then there must be a point between the edges of that interval, so between, in this case, 0 and 3, such that the derivative at that point is the same as the slope of the secant line. Let me bring up this, and I'll just throw a secant line in here, and I'll draw the secant line in blue this time. There's our secant line, and mean value theorem just says there must be a point on this curve between 0 and 3 where the derivative is the same as the slope of that secant line, and you can see there is a point whose derivative is the same as the slope of the secant line. There you go. So that's the visual of the mean value theorem, or the average slope theorem. So let's go ahead and verify that we can use the mean value theorem. The verification requires two steps. The first one is to showcase that our function is continuous. Well, f is continuous on all real numbers because it's an exponential function. Remember, all of our functions are continuous on their domains. So f is continuous on the real number system implies f is continuous on the given interval, which is, I think, 0 to 3. That was supposed to be on 0 to 3. Also, f prime of x, which is equal to a negative 2 e to the negative 2x, exists for all real numbers, which implies f prime exists on the open interval 0 to 3. That's all. Those are the only two conditions you need to use the mean value theorem. Now that we have those two conditions met, check and check, that means that there is a point between 0 and 3. In fact, I'll write this down. There exists a point between 0 and 3 such that f prime at that c is equal to the slope of the secant line connecting the edges of that interval. That's the blue secant line, and there's basically some point c whose derivative at that point would match the slope of the secant line. So let's go ahead and write this out. We want f prime at c. Well, f prime at c is equal to e, oops, no it's not, it's negative 2 e to the negative 2c. f of 3 is e to the negative, what is f actually? E to the negative 6, so I'll just write that in there. F of 0 is e to the 0th, which is 1, all over 3 minus 0. And we could solve this for e, or for c, sorry. I'm gonna clean this up a little bit first. Negative 2 e to the negative 2c is equal to, I'll multiply numerator and denominator of this by e to the 6th. I just want to. So that's 1 minus e to the 6th over 3e to the 6th. You don't have to do that. I just wanted to do that. Then I'll divide both sides by -2. So I get e to the 6th minus 1 over 6e to the 6th. Again, I divided by a -2, but I moved the negative into the numerator. And now I'll take the natural log of both sides. So you get -2c is equal to the natural log of e to the 6th minus 1 over 6e to the 6th. And then finally, one thing you should note here, by the way, that argument of the natural log there is positive. E to the 6th is massive. -1, well, I shouldn't say massive. E to the 6th is large, -1 is still positive, divided by positive, so that's a positive number. And then divide both sides by -2, and you'll get that c is equal to a -1/2 natural log of e to the 6th minus 1 over 6e to the 6th. And I suppose you could technically move that -1/2 into the exponent and take a reciprocal. So this is technically equivalent to, though you could stop right there, it's equivalent to the natural log of the square root of 6e to the 6th over e to the 6th minus 1. But most people probably wouldn't do that last step. So anyhow, this is that value of c, where the derivative of our function matches the slope of the secant line. So it's a very rote example. That's how it's done. Make sure you state your function's continuous. Make sure that you showcase that your function, its derivative exists on the open interval. And then just solve f prime of c is equal to the slope of the secant line. Another use that's commonly, another problem that's commonly given for the mean value theorem is finding upper bounds on functions. And this I've often found as a student and as a teacher, I found that this is kind of a really silly example, but it's just typical. You'll see them, so I thought I'd cover it. Okay. So let's suppose that we have a function where f of 0 is equal to 1, f prime of x is always less than or equal to 2 for all x in the real number system. Now, let me just tell you that right there, that little statement, f prime is less than or equal to 2 for all x in the real number system, tells us our function's differentiable everywhere, which means it's continuous everywhere. So that tells us we have continuity, f is continuous, and f prime exists. So that's just an important little statement that just allows us to use the mean value theorem. We're being asked to find an upper bound on f of 3. Okay, well, let's see. If I can use the mean value theorem, then I could say the following. On the interval from 0 to 3, and by the way, I chose 0 and 3 because those were the x values they gave us. F of 0, f of 3. So on the interval from 0 to 3, there must exist a c such that f prime of c is equal to the slope of the secant line connecting 3 comma f of 3 to 0 comma f of 0. I hope that makes sense so far. That's by the mean value theorem. And we often use MVT for mean value theorem because you'll write that so many times your hand will hurt. So you might as well just write MVT. Well, this would imply, if I write it in its alternate form, this implies that f prime at c times the quantity 3 minus 0, which I know is 3, don't worry about that, is equal to f of 3 minus f of 0. Well, this implies that 3 times f prime at c plus f of 0 must equal f of 3. Now remember, the reason why I'm doing this is because we want to find an upper bound. Like, what's the largest that f of 3 can be? So how are we going to find that? Well, I'm going to just say, but f prime of x is always less than or equal to 2. In other words, f prime of c is always less than or equal to 2. Now I find that this is probably better written as follows. So I'm going to say f of 3 is equal to 3 times f prime at c plus f of 0 But we know that f prime at c is less than or equal to 2. This is like a substitution, essentially. Because we know the derivative here is always less than or equal to 2, then this expression here, 3 times f prime of c plus f of 0, is less than or equal to 3 times 2 plus f of 0. And that's 6 plus f of 0, but we know what f of 0 is because they told us at the very beginning. That's just 1. So 6 plus 1, or 7. So this implies that f of 3 is less than or equal to 7. In the worst case scenario, it'll be 7, right? It could be less than that, but in a worst case scenario, it's 7. So this is kind of, again, a trivial use of it, but that's an upper bound of f of 3. It's a trivial use of the mean value theorem. However, it is a use of it, and you'll see that within calculus textbooks. Now, as far as the mean value theorem goes, and examples in textbooks, this is what I think covers the vast majority of them. The next video will cover these really cool consequences of the mean value theorem.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.